That was nice. It said that very gently. Well.
Yeah, what, that's fine.
All right. So we've gone through basic sort of considerations and some screening, and a lot of the stuff that we're gonna do this semester and screen for your regression models is gonna be exactly the same thing, looking at distributions, box plots, things along those lines. But when we get into the actual correlation or the actual regression model, there's outputs from the regression that we're gonna have to go through and take a look at to determine accordance with assumptions, okay?
A really nice haiku, Josh.
It is a really nice haiku. I didn't write it, I found it. But I'm gonna be really upset if my rigged situation here is no longer something like this.
Linear, I don't know. It is.
Oh, I love
So I got like linear versus just.
There we go. Okay, perfect.
I'm good on.
All right. So basic assumptions of our regression models, okay? These are the things that we need to keep track of, okay? First assumption is that our predictor variables, our x's, are fixed non-random variables measured without error with variance greater than 0. Okay, so there's a lot of stuff packed in here. One, we're saying that we're measuring fixed variables. Okay, we'll talk about what that means. We're measuring non-random variables, fixed non-random variables, measured without error. Okay, so we've measured them perfectly. There's no error in our measurement. With variance greater than 0, it means that we just don't have constants. Okay. Anybody have a problem with that first assumption? What do you think, Emma?
There's always error when you're
Yeah,
measuring
you
your
know,
variables.
stuff there, right? So already, right, like in a vacuum, our regression models work well, so long as we don't have error in our predictors. But we do have error in our predictors, so already we know we're gonna have violations just right off the bat, okay? We're saying that our errors, okay, these are our residuals, have normal distributions. Okay, so if I were to look at how far off, right, remember that our residual is determined as the deviation from our predicted value versus our actual observed. If I look at that, the idea is most of them are going to be sort of centered like around 0, right? Or very close to 0, right? My prediction model is capturing stuff. It's obviously not going to capture the actual observed value for everybody, but the distribution of those residuals is going to be sort of reasonably normal. We're going to have some where I overestimated, some that I underestimated, some that I really overestimated, some that I really underestimated, but we've got a nice normal distribution for those residuals, okay? We're saying that the variance of our errors is constant for all variant values of x, okay? What this means is, so let's say I've got my extroversion score that's going to go through and predict things, right? What I'm saying is that my distribution of my variance is not dependent on the value of my predictor, right? This gets into homoscedasticity assumptions, equal variances for a fixed x. So as my x increases, right, the variability of my errors stays the same. It doesn't get bigger and bigger and bigger as my values of my predictor get larger and larger and larger. Okay, we'll talk about what that looks like. Yeah.
About, I guess, what you mean by variability of errors, because is the error in this context just, is it just what we're not accounting for with x? Like,
Yep.
Okay, thank you.
Yep. This is sort of our error is anything that's creating variability in our outcome that's not attributable to something in the model, right?
Okay.
Error is anything like, and this could be random error, just because people are different because they're different sometimes. It can be due to unmeasured variables, right? It can be due to systematic biases and things along those lines. But the assumption of the model is these errors are normally distributed and have equal variance throughout the distribution of our predictors. Okay. Okay. We're also assuming that our errors are independent of one another. Okay. If the model goes through and predicts all our score on how much we like pizza, right? The prediction model, how far it's off for me is unrelated to how far it's off for Helena or Emma W or Laura or anything else, right? Everybody is their own independent thing. There's no residual dependency in terms of our residuals, autocorrelations, things like that. We have certain designs where this is not going to be the case, and then this becomes a problem for the estimation assumptions and regression. Okay. We're also assuming our errors are uncorrelated with our observed values of X and that our expected value of error in the population is 0. Okay. These are 2 in red because we can't test these. Okay. These are things that we have no way of assessing within the data that we have. But there are some things that sort of we can think about if these are violated and sort of consequences that come up and things. We'll talk about those. Okay. So if we're going through and thinking about some basic terminology within regression, things that you'll come up, you'll hear things, and this is important to know because you'll see this in the literature, that our regression models contain the best linear unbiased estimates. Okay, this is you hear these referred to as blue when we have assumptions of 1, 3, and 6 are met. So if I have fixed non-random variables and I have homoscedastic errors, independent error, observed X, and 0 population error, then my estimates are the best linear unbiased estimates. My estimates are blue. Okay, this is a good thing. So we get less concerned about this in psychology than sort of other things, but something to be aware of. Residuals meeting assumptions of homoscedasticity and independence. We refer to these as independently and identically distributed residuals. Okay, so the distribution of my residuals looks the same across all levels of prediction, and they're not sort of getting larger or sort of more narrow, sort of as we're working back and forth. Okay, normality of errors here is required for the unbiased estimation of my standard errors. Okay, this is what's going to happen. A lot of times as we're working through this, you'll notice a trend. When I do violate my regression, my basic regression assumptions, what typically happens is it F's with my standard errors. Okay, my actual coefficient is not unbiased. My coefficient is fine. And we talked about this a little bit with multicollinearity, right? Talked about if I have a situation where I have multicollinearity, my actual estimate is unbiased, right? My estimate is fine. What happens if my standard errors start to get screwy? And if my standard errors are screwy, what does that do to my statistical tests? Throws those off, right? That whole nice system that makes me be able and very confident in sort of interpreting my p-value as sort of evidence against that, like all that goes out the window, right? Because my standard errors start to get unreliable. Okay, and if my standard errors get unreliable, my statistical tests are problematic, right? I don't have as much faith in those. If my standard errors are messed up, then my confidence bounds start to get real screwy, right? And so this is where we tend to see problems with some of our assumptions. Okay, so as we're working through these, not just wanting you to understand what the assumption is or how we go through and test the assumption, but also if I violate that assumption, what are the potential consequences? Okay, and this is probably the most critical thing because you're always going to violate assumptions. Because data is messy and real life doesn't work in a vacuum, and so this is always going to be there's always going to be stuff that comes up. Your job is to say, okay, what are the potential violations? What are the potential impacts in terms of me interpreting things about these data? Okay. And so again, when we're going through and thinking about these individual assumptions, and I'm going to work through each one of these so that you understand kind of what's going on and what we're doing. This is just kind of giving you a quick overview. 2 things I'm worried about if I violate an assumption. 1, what's the impact on my regression coefficients, right? My understandardized values, my standardized values, do I have trust in those? Right? Are they giving me an accurate representation of the expected relation of X or the unique effect of X on Y, sort of based on my model? And oftentimes, our regression coefficients are fine. Okay. The other question we have to ask is whether or not the standard errors And my mean squared residuals are unbiased, right? As sort of the nuts and bolts of my error, this starts to become important when I'm going through and running tests for individual coefficients for my model R squared, things along those lines. If all I'm doing is predicting outcomes, okay? Again, let's say, Lucy, you run Lucy's Crab Shack, and all you want to know is how many crabs you're going to sell sort of next quarter, right? Like, what's your income? You don't worry about any of this for a lot of stuff, because if all you're trying to do is predict the dollar amount, and you don't like worry about like tests of individual predictors and things like that, most of this stuff you're not going to have to worry about, because all you're trying to do is get the best prediction of your intended outcome. You don't know, you don't care why it predicts, you don't care what specifically predicts. You just know if I just throw these things in there, I get a pretty good estimate of what I'm going to spend next quarter. A lot of this won't matter to you, right? But that's not the space we live in social science, right? Like a lot of the times, like I have a specific hypothesis about this specific predictor and how it should relate to this thing or other stuff. Now, all of a sudden, though, we're banking on our statistical tests to tell us whether or not we have evidence that that coefficient is something different than zero, hopefully in the direction that we predicted it. Now, all of a sudden, those tests start to become really important. And so the standard error stuff starts to become really critical in terms of having confidence in our results. Kind of understand kind of why we need to be thinking carefully about our assumptions and sort of things that are going on with that. This is my best stat comic ever. It makes me laugh. And what a terrible day to record things.
He's so cute.
So classic.
I do love this.
This pains me, but I love it.
Right? It's fun. It's good, right? Nobody can hurt you in other ways. It's very ominous. All right. Back over here. Okay. Want to start talking about our fixed effects assumption. Okay. Again, we're saying that our predictor variables are fixed non-random variables measured without error with variance greater than zero. Okay. Remember, we talked about this a little bit before. Our fixed effects model assumes that our predictors have specified values that we've systematically pulled so that all possible relevant values are captured in all subsequent replications. Okay. The idea behind this, and again, a lot of our science came out of like old school experimental types of things, right? And Danielle, if you're running an experiment and you're saying like, here are the 4 conditions that are necessary to test this hypothesis, anybody else who would ever go through and do this would have these 4 conditions, right? Then your predictor variable is conditioned and you have all sort of stuff you've systematically placed to randomize people into these different conditions. You've got a fixed effects model, right? If I'm looking at, again, so what this would imply then is if I'm looking at the impact of extroversion on some outcome, if I had a fixed effects model, it would mean I've systematically sampled people for all possible levels of extroversion that anybody could ever want to or be interested in ever using moving forward. And what I've done is I've gathered people from each level of extroversion across the whole dimension, and everyone is represented in equal amount, not necessarily in equal amounts, but let's say equal amounts in my sample, right? So let's say there are 100 possible scores for extroversion that you could get on this measure, and I've systematically pulled 20 people from every single level, and those are the people who are going in. There, I have a fixed effects model where I have extroversion as a fixed variable. Okay, and with my fixed effects regression, makes no assumption about the distribution of my predictors, right? Because if I go through and I systematically sample and pull individuals from every single value, do I have a normal distribution of extroversion? No, I don't. April, what does my distribution of extroversion look like?
If you have the same number of people for every level, it's
Yeah.
just gonna be square.
Yeah, it's just a square distribution, right? And so for classic regression model, we have no assumption about the distribution of my predictors, right? Now, if I were to do it, or maybe I just go through and make sure that I've got representation for all possible values that anybody could be interested in terms of regression, but I don't sort of systematically make sure that I've got the same amount for everybody. My distribution could look like it's all over the place, right? I don't know what it's going to look like, but I've captured at least a handful of people across all possible values. So I don't know what my distribution is going to look like. It's probably not going to be normal, but at least I've got sort of something there. So with my fixed effects regression model, there is no assumption about the distribution of your predictors, right? And so this is something you'll see. I don't know. I've posted a review I did on a paper that sort of people got. They thought they had something, they didn't have something because they got really excited about all these people getting concerned about the sort of distribution of your predictor variables. And they said, well, you don't have a normality assumption for your predictors in regression. And that's true so long as you're running a fixed effects model. Do we ever run true fixed effects models when we're doing this stuff in psychological science? We absolutely do not, right? What we do is we go through and we end up with a random variable. Okay. What we do is there's just folks out there in the universe who I invite into my study. And whatever level of extroversion they have is the level of extroversion that gets sampled in my study, right? Am I going to have someone who represents all possible versions of levels of extroversion in my study? Probably not. Most people are probably going to be right around the mean, right? Some people are going to be higher, some people are going to be lower, but I don't worry about going through and systematically gathering every single person who could represent every single sample. What I do is I just let people come in. And so now all of a sudden is what I have is a random variable. Okay. Here I've got, these are all the colors of gumdrops in the world. And I made sure that I've got 10 of each one of those, all possible colors of gumdrops that anybody could ever conceive of in the universe are all contained in here, right? If I looked at the distribution of color of gumdrops, as April said, it would be exactly square. Everything is captured in there, right? But that's not how we do things. What we do is we collect our variables as random variables. And as soon as we switch over into that random variable model, we've violated sort of first thing right off the bat, okay? So just the way we conduct science is a violation of basic assumptions of regression. So this is not what we want. This is what we want. But this is what we get. So we need to go through and think about what are the impacts and how do we go through and work with this. Okay. So again, because we know this fixed effects assumption is nearly always going to be violated in practice, unless you're using a regression format for like some experimental research where you've gone through and all your IVs are randomized assignment types of things, then you're fine. Then you're fine, right? For the stuff that we usually do, we're using random variables for our predictors. And so, but this is fine. We can still use our regression model with random predictors so long as my predictors are multivariate normal. Okay. And this is what we talked about sort of last week, right? Talked about our data. We assume that our data are multivariate normal. The distribution of all variables and all linear combination of variables or all combination of variables are linear and homoscedastic. That's what we need to happen, right? So think about this as sort of creation story and Adam and Eve, original sin, everything goes, it's fine, so no problems until we go through and we violate this one assumption. Now we got a whole bunch of rules, right? Now, in sort of basic regression, no assumption about the distribution of predictors. Now, because we are using random variables instead of fixed variables, now we do have to be concerned about the distribution of predictors, because if we don't, if we have data that are not multivariate normal, now we go through and have impacts on our estimates. People understand kind of sort of the original sin of regression as we practice it in psychology and most social sciences and other places. Okay. So this is the fixed effects piece of things. We're also assuming that we measure our predictors without error. Okay. If we get into old school classic measurement theory, right? This is going back to like my graduate work, sort of working with Dr. Sims in Buffalo, right? Talking about sort of basic measurement types of things. We can think about it in a classic measurement setting as my any observed value that I have of something is going to be a function of the true score and error, right? There's some unknown level, right? If I go through and I'm measuring, I'm interested in kindness, or let's say resilience, okay? And I measure you and you sort of go through and you sort of give me a score and I say, this is Emma's score for resilience. That score is some combination of that latent true level of resilience plus error, whatever I should have missed and didn't capture with that. What we assume in our original with classic regression is that we've measured our predictors without error, okay? Now we know that this never happens, right? So again, what happens if I measure my outcome, my sort of y variable with error, it doesn't create problems with biases in my actual coefficients, but what it does do is it inflates my standard errors, okay? So again, there's not an assumption about your y outcome. You can measure y. Classic regression says you can measure y with error. It doesn't bias your estimates. What it does is it inflates your standard error. Okay. And so if let's say that I'm going through, Elaine, and you've got your thesis you're putting together, and you like this is the thing that I want to go through and measure on. What are you measuring on your outcome? What's that?
Personality functioning.
Personality functioning. Okay, so you got this measure, and let's say, boy, I've got this measure, but it's sort of like, I don't know, I'd have to do some digging and I have to email someone to get it or something like that. Or I could just make up a 5-item thing on my own, right? You could do that and you would measure probably get at some piece of personality functioning, but you probably have a whole lot more error, right? And if we're thinking about error in my outcome as resulting in inflation in my standard errors, what did that just do to the power of your study? It dropped it down, right? Because if my standard errors get bigger, all my tests are going to get smaller, right? And so again, from a basic measurement standpoint, thinking about, even though I don't have errors or assumptions about measurement with error in my outcome, it still starts to become really important, because if I've got a good tight measure, it's just cutting down the static. And so it's going to give me a stronger test, right? We don't think about this enough. There are very, very real impacts on choosing messy measures or just making stuff up on our own. Sometimes you have to do that, right? But it's something we should think more carefully about, okay? Now, measurement in X does create a bias in my parameter estimates, okay? As soon as I have measuring my predictors with error, it does go through and starts to impact my parameter estimates. So again, if we think about so this beta or sort of B, y given x, this is just your coefficient for an individual regression coefficient, right? This is the regression of x on y. And thinking about this in terms of classic test language, we can think about my observed coefficient here as being a function of the actual true population parameter multiplied by your reliability, okay? So alpha x is representing the reliability of your x measure there, okay? So thinking about who can I pick on? Who has worked with reliability indices before? Something else. Where do reliability indices sort of range? Elena, you are working with Casey stuff like sort of reliability. What's the reliability of a measure if I'm measuring reliability?
Like what kind of what?
Yeah, we're just saying sort of from sort of what are the numerical ranges that a reliability coefficient can take? Do you know?
Oh, like from 0 to 1.
0 to 1. Okay. So if I have a internal consistency estimate of sort of 0.8, I'm feeling pretty good about that. That's kind of like the league standard, right? We're like, okay, that's okay. Or if I have a test reliability of like 0.3, I'm like, yikes, that's maybe not so good. All right. But mathematically, if we're thinking about your observed coefficient, right, as a function of your population coefficient multiplied by your reliability, as that reliability goes down, what happens to your observed coefficient? If I start multiplying a number by smaller and smaller decimals, what happens to the output? What's that? Your output,
Oh, it's,
it goes down, right? So if I go down, and so you can do this, pull out your calculator, right? So say my coefficient is 2 in the population, and I multiply that by 0.8, see what you get. And if you populate it, multiply it by 0.5, see what you get. You multiply it by 0.3, see what you get, right? What happens in function is if we have error in the measurement of our predictor values, what it does is it attenuates our estimate of that association, right? As a direct function of sort of the reliability of the measure. As I have more static, more error in my measure, what it does is it attenuates sort of the estimate of that relation. So anytime I'm measuring things with error, if this coefficient for reliability is anything less than 1, it's starting to sort of reduce your outcomes here, right? So again, thinking about what's happening here, my observed value is only going to be equivalent to the actual population value on the whole, so long as I'm measuring my X's without error. As soon as I introduce error into that, the estimates that I'm getting are going to be underrepresented of the population systematically because I've got more fudge going on there. So the estimates that I'm seeing are going to be weaker than what likely the population estimate is going to be. Okay. So once again, thinking very, very carefully as you're conducting your research, as you're choosing things, sort of Jen and I and Lucas are going through in our big sort of interview data, stuff like that. And we just spend so much time trying to make sure everything's entered correctly and everything's sort of, but it has an impact on sort of your output, because if you've got a bunch of error and sort of wild stuff going on there, it's going to screw with your standard errors. It's going to attenuate your estimates. It's a big deal. Okay. So we're thinking about this from a practical applied standpoint. Measurement error is going to increase your residual variance, and so it's always going to attenuate your model R squared. Okay, your model R squared, your sort of estimate of model fit, is always going to be smaller as a proportion of how much error you've gone through and thrown into your measurements. Okay, if you're so this is going to be sort of what happens in a one predictor case. In actual fact, when we go through and look at the impact on our coefficients, it starts to get complicated because you've got sort of more variables coming in multivariate space. And so the impact on your individual coefficients for your individual predictors is going to be impacted by the error of your measurement of that specific X variable, also how those measures relate to other variables that you have in your model. It gets pretty tricky, but just know that in general, the assumption should be is if I'm measuring things with error, it's going to negatively impact my estimates. It's going to negatively impact my standard errors. It's going to make it harder for me to go through and find the effects that I want to find, right? And we'll see this, a very real example of this when we get into some moderation stuff, okay? If anybody asks you, how many people do I need for a moderation analysis? Tell them 500, because that's probably about right, you know. But we'll talk about kind of the nuts and bolts of what's going into that, okay? That's it. Do I have 500 observations and anything that I've run in terms of moderation? Absolutely not. But I'm just saying that it's if you want to have it adequately powered, that's kind of what you're looking at. Okay. So this was a lot of time spent talking on this first assumption, but do people kind of understand sort of the math, the logic behind kind of what's going on with this? So again, remember that this is how this model operates in a vacuum. But it never turns out that way actually in practice, right? This is a fine thing to look at on a shelf when we actually pull it out and start using it. We have to be thinking carefully about, okay, where have we gotten nicks and dings, and so what's going to go through, what's the likely impact on my outcome, and then how do I go through and interpret that? All right. Second assumption, okay, is that we have normally distributed, our errors are normally distributed, okay? This is a basic assumption for our statistical tests for multiple correlations, regression coefficients. This is kind of a big one. If we violate this, what happens is our standard errors start to get wacky, and we start to lose confidence in those p-values, those tests that we've gone through and done. In order for those to be accurate, what we're assuming is that the distribution of our residuals is normal across the whole prediction model. Here, we've got an example where we have a predictor X, a predictor Y. here's my regression line, and you'll see that across all values of X, what we tend to see is, are those values kind of stacked up on the line. And then as they start to sort of get farther and farther out, they kind of spread out. We've got a nice normal distribution of our errors. And these errors are also constant, which we'll get to in assumption 3. Right? We can start to see non-normal errors on our regression models due to things like sampling strategy. Okay, let's say I only sample severely depressed individuals. Okay, so I'm going to go through and I want to look at the relation between, say, where you're looking at people, looking at the relation between depressive symptoms and functioning, right? And so you only sample people who are like super, super severe. Okay, and if we're looking at the relation between severe depression and functioning, where are people mostly going to operate if they have severe depression? Are they going to be functioning real well? No, right? So if we got functioning, we're going to have a floor effect, right? There's only so far, like I got 0. There's nothing, I can't get less than 0 on functioning. It's 0. So everybody's going to be stacked up down here at the bottom. But if I miss, if I can't go down, where's the only direction I can miss in? Up, right? So I may have people in this sample who generally are not doing well, but if they're doing all right, right, it's up here. So now I've got a distribution of residuals where everybody's kind of stacked up on the line down here, but when I miss, I always miss high, right? And so what's the distribution of my residuals in that situation? Everybody's stacked up around 0, and the only way I miss is if people are sort of functioning higher than what I would predict. What's that distribution look like, Lucy?
I was trying to figure out which would be the skew.
Yeah, it's going to be skewed, right? So I'm going to have a skewed distribution of my residuals, right? And so what now is the relationship between depression and functioning? Is that going to be an inherently skewed model? But no, but if I only sort of specifically get people who are sort of not able to leave their room or things along those lines are scoring very, very high, what I've got is a methods issue, okay? Other thing that can happen is I can get, again, true population distribution. Like I got this from the book, Heroin Use in Children. How many little kids use heroin? Probably not a whole lot. So we've got sort of mostly 0, but then some people probably do at a very young age. And so it's going to skew high, right? And so this is what we need to go through and be taking a look at to see if we've got a situation like this, it starts to impact my standard errors here, okay? So again, let's say here's depression and life satisfaction, right? Most people are sort of this, if this is a sort of highly depressed group, most people are operating down here, right? Here's my best line, right? But if I'm missing, it's people are going up here. So what I end up with, if I look at my residuals, I've got something like this, right? Most of my residuals are down here close to 0, but if I miss, everything's positive. And so what I've got is a skewed distribution of these residuals. And so again, here what we're talking about is a floor effect, okay? What happens is when my model guess is wrong, people are systematically overperforming my model because they can't underperform because I hit the bottom. There's nowhere for them to go farther down. So I don't have this nice normal distribution where sometimes I miss highs, or sometimes I miss low, sometimes I miss high. We've got a nice distribution of things. Okay. So if I have skewed residuals, what's going to happen? My regression coefficients are then, once again, not going to be impacted, right? My regression coefficients are going to be unbiased estimates of the population parameter. But what I'm going to have is I'm going to have depression in this case of my standard errors. If my standard errors are too small, what happens to my tests? What do you think, MH? Yeah, it's too big. My t-tests for all my things are too big. They're too large because the standard error is too small, right? Now, you might think back, oh, this is a great thing for power, right? But that's not great, right? Because it's kind of cheating and, you know, you're sort of likely to be making claims that are maybe not supported because what you're actually seeing is your results are being driven by a violation of your model as opposed to what's actually happening out there in the okay? And if I've got a small sample size, we'll also see depression in the standard error of my R squared value. I don't worry about this as much. Anybody have an idea for why I might not worry about standard error of my R squared? Do I care about R squared all that much in psychological science? Not really, right? R squared in undergrad statistics kind of a big thing back, oh, this is your R squared, it's your model R squared, and your test of your model and sort of things along those lines. But again, our goal with our research is rarely to maximize our R squared. We should be thinking about it more, but our R squared is often not the thing we care about. And what does a test of R squared tell me? Let's say I have a significant R squared. Well, if I have a significant R squared, what does that mean? What do you think, Elena?
It's like the model fit is like significant.
Okay, and anytime I say something significant, what does that mean? What's that?
It's not zero.
It's not zero, yeah. All it is a test that my R squared is not zero, right? And if I got enough people, do I care that my R squared is not exactly zero? No, it's not a useful test, right? So people get, now if I want to go through and I have a model that sort of accounts for 3% of the total variability of my outcome, that's not a great model. There's a lot of stuff. I'm not capturing much of the predictive value. So it's just not good, right? So then if I had a non-significant R squared, I might be concerned. It's just like I just put together a poor model. I have a specification issue because the things that are in my model aren't in the model, and I need to probably think about that, right? But rarely do we care about the significance of your R squared value, right? It's generally going to be something that's very clearly not zero. Your statistical test is just telling you that it's not exactly zero. It's not really sort of an interesting or something that we care about a whole lot. Even if I'm just trying to predict, I still don't care about it because I'm not like, hey, for Lucy's Crab Shack, I put you together a predictive model that predicts something that's not zero variability in next quarter's outcome. Are you going to be signed up for? You can pay me a lot of money for that? Probably not, right? You're going to say, what is it? I'm more interested in the actual value on not whether or not it's different than zero, right? So again, yeah, this will happen, but we generally aren't super concerned about it. Okay. Questions about the distribution of our residuals? Okay. What we also need to see is constant error variance of our residuals. Okay, the variance of our errors are constant for all values of X. Okay, this starts to get into the same type of idea of the homoscedasticity stuff that we talked about last time. Okay, the difference here is that we're talking about the homoscedasticity of your residuals and not your observed scores. Okay, and so what we need to do is we need to go through and run our regression models to get our residual values, and then we can go through and look at distributions. Yeah. Okay. So again, what we can start to see is measurement error creating problems with heteroscedasticity, right? We talked about these achievement tests start to get less reliable as scores get higher and higher and higher, right? And so is my my estimated value of my predictor, if it's IQ, starts to get more and more messy. What I'm likely to see in my errors is things get sort of more and more spread out. So down here at the bottom, right, we're sort of kind of in the bell of the normal curve here, right? I'm pretty good, and so I have some errors, but as I get bigger and bigger and bigger values, my errors get bigger and bigger and bigger. They start to spread out. This is where we're starting to see, we might see evidence of heteroscedasticity. Other thing too, if I omit relevant variables, right? We talked about this, the relation between age and income. Now, if I'm looking at 8-year-olds and their income, that's going to be pretty tight. If I look at 16-year-olds and income, it's going to be tight. By the time I get into people in their 50s and 60s, it's going to be all over the place. Some people are going to make not a whole lot of money. Some people are going to make a ton of money, right? Is the variability and the spread of that error is going to be way, way bigger, right? What did we say we might go through and include to account for some of that heteroscedasticity? If I'm looking at the relation between age and income. Was that MOW? What do you think?
Oh no, I was a little, like, I just,
Yeah.
just said what to myself.
Yeah, like,
Can you say the question
yeah,
again?
yeah. So if we're thinking about, as I look at the relation between age and income, and I see my errors spread out, right? Because I get more and more errors that you go through. What's another variable I might add to that model that helps sort of reduce some of that spread?
Education.
Education, yeah. So certainly I'm probably still gonna see some spread because everybody at sort of 16 is probably making a minimum wage for the most part, things along those lines. It's not gonna get rid of everything, but again, if I start to throw in, say, education, sort of some other employment factors or something along those lines, what it's gonna do, it's gonna narrow that down quite a bit, right? So that's one of the things when we see heteroscedasticity in our residuals, one of the things we probably, and for me, probably the first thing I would want to be thinking about is, well, one, what's the distribution of my measures, because that can cause problems. But then two, do I have omitted variables? Are there variables that should be in this model that I haven't accounted for that would account for why, as this predictor increases, I get less and less accurate at predicting the actual observed score? Yeah.
Why the why there's a difference between the homoscedasticity assumption and the equal conditional variance, because isn't the
Oh,
residual,
no, they're the same thing.
oh,
Yeah.
they're the exact, okay.
Yeah, it's the same thing. Yep.
Okay.
Good question. That's right. If there was, I would have some explaining to do, but it's not because it's the same thing. So, yep, you're exactly right. Other questions about this? All right. So what happens when we violate this, right? Once again, my regression coefficients are fine. But what happens now is we see biases in my standard errors that are going in the direction of the relation to the error in the predictor. Okay. So as my error variance increases, as my predictor increases, right? So you see this span sort of kind of going out this way. What happens is it depresses my standard errors. Standard errors get too small. My test statistics get too big. I'm claiming that things are holding unique relations when they're actually not. If we go the other way, if my error variance decreases as my predictor increases, so I start with a ton of variability and it sort of narrows down, kind of funnel shaped the opposite direction, what I'll have is I'll have inflation of my standard errors. Standard errors are too big, makes my test statistics as a result are too small. And so there are things I'm going to be making type 2 errors because I'm not detecting things that I might normally if I hadn't had a violation like this. It's easy to see in kind of the one predictor case as we start to get multiple variables in. We start to get into sort of multi-dimensional spacing. It's harder to see, but we'll go through and show you how to go through and sort of plot these out so you can go through and test some of this stuff. Assumption 4 is that I have independent errors. Okay, what we're assuming is how much I miss in terms of my prediction for one person is unrelated to how much I miss for somebody else. Okay, and anytime I have dependency in residuals, what is this? We refer to this as autocorrelation, right? The error for Lucy is related to the error for April, is related to the error for Emma, related for the error of Lucy, so, or excuse me, Laura. So we've got things sort of kind of all tied together here. Okay. A couple different types of autocorrelation that we can see. If I'm looking at observations of the same person over time, what I'm going to get is temporal autocorrelation. Okay. Danielle, if I go through and I measure your mood on, say, like the PANIS, right? If I measure you right now, and I measure you next week, and I measure you the week after that, and I measure you the week after that, you're going to have some relation between those, but it kind of depends on how I capture you that one day. It's going to be pretty stable, but you're going to have some variability, right? What happens if I go through and instead of sampling you once a week, I sample you every hour over the course of several weeks? What I'm going to get if I still look at your score at week 1 and week 2, they're going to be kind of correlated. But if I look at your score for hour 1 and hour 2, those are probably going to be highly correlated, right? And so what we have is we have certain observations are going to be more closely related to correlation or observations that are closer to them in time as opposed to things that are more distal. And so what we have is a temporal autocorrelation with this, and that creates problems because there's dependencies going on in there. Okay. We also have observations that are made in similar environments. We have to worry with spatial correlation. Okay. So MH, if I were going through doing school-based stuff, and you're looking at behavior impacts or sort of impacts of an intervention on behavioral outcomes in school-age kids, right? Presumably, you're going to be working in classes, right? But you got a number of different classes across a number of different schools, right? And so you're going to go through. You've got an amazing dissertation. Everybody's super excited about it. You know, I'm going to regression the hell out of this. Problem is, what we've got is we've got a sort of structural autocorrelation thing going on here, right? Because for all those kids in the same classroom where the intervention is being implemented by the same teacher in the same environment, the impacts of those kids are all going to be more similar to one another than any random student from that classroom and a student from another classroom, right? This is where we get into nested data, which causes problems for our regression models. And what happens are our regression models start sort of blowing things up, p-values all over the place and things that everything's related, when in fact it's not. It's sort of everything's being inflated by this spatial autocorrelation. So this is where we have to get into types of analyses that account for the nested structure of those data that model this specifically. And then we have appropriate standard errors and appropriate tests of what we're going through and doing. Okay. So again, once again, same old story. My regression coefficients are fine. It's just my standard error estimates that are happening. And what happens is my mean squared error from my overall R squared, my individual standard errors can start to become substantially underestimated. Okay. So again, if you see someone who's writing a paper and there's obvious, just based on the design, spatial autocorrelation where they've got nested data and they didn't account for it, and they're super excited about all the stuff they found, like, well, yeah, no joke. So your standard errors are tiny because it's being suppressed by sort of the dependencies in your errors. And so things are going to pop up all over the place, right? So again, as we're going through, we obviously like to find things in our data, right? But we shouldn't like to find things in our data that aren't really things in our data. They're just a function of a violation of assumption. This is kind of what's going on here. All right. Questions about this? All right. Another assumption of our regression models is that our errors are uncorrelated with my observed values of X. Okay. What happens here? This is a direct product of having a properly specified model. Okay. And my model is correctly specified if one, I have all predictors that need to be in my model are in there. If I have there's no irrelevant predictors, nothing that shouldn't be in there is in there. And the form of my model is correctly specified, right? If I'm running a linear model, what I'm actually doing is there's an actual linear relation in the population for me to go through and identify, okay? Do we often work with correctly specified models? Probably not, right? Just because there's just so many things that go into determining behavior. Behavior is multi-determined, right? Lucy, if you're looking at eating pathology and stuff like that, think about all the things that go through and start to influence sort of people's behavior within that, right? Technically, what we should have are models that include all this stuff in there. Even if it doesn't, if like I'm not actually interested in these things, if these are things that are supposed to be in the model to account for whatever I'm looking at, I should probably still measure those and have those in there, even though it's not something that is maybe the focus of my research. Okay. Now, if I go through and I do this, right, and think about same thing for like Jenna and I's working in trauma, right? If we go through any regression model I work with trauma, participants, sex, gender should be in there because we know women are at higher risk than men, right? That's accounting for that's a very well-known thing. So any time you don't have that in a model is a misspecification because you know that should be in there, right? Trauma history, trauma low, which is kind of what Jenna is looking at, should 100% be in there because we know you can only get kicked in the guts so many times before you start to sort of wear down a little bit, right? So that should be in everything, right? So if we think about all the stuff that we should be accounting for in our model where we don't, like, well, I'm not interested in that. I'm just interested in this thing. That's fine. It makes for a more parsimonious model, right? And I don't think we should be stacking our models with a bunch of stuff that's irrelevant. But if we know based on theory and sort of conceptualization of the stuff that we're measuring, probably should have some indicator in there, right? One, it's going to impact it's going to be helping out with this assumption, and then two, what it's going to do is it's going to be accounting for more of your variability in your outcome, right? And if my R squared is higher, I don't necessarily care if my R squared is equal to 0, but if my R squared is bigger, that means I've accounted for more things in my outcome. If I've accounted for more things in my outcome, what does that do to my error term? Shrinks it down, right? And that goes through and drives my standard errors. And so what I end up with is a more powerful model if I've gone through and I've accounted for things in the thing that I'm trying to account for, as opposed to just throwing in here my couple pet variables that I want to take a look at. You can do it, we all do it, but in terms of like actual good statistical practice, it's a bad idea for a lot of reasons, right? So this is where, particularly with, and if we're working with existing data, right, there's only so much we can do because the variables we have, the variables we work with. But for you all working on theses and dissertations and things like that, thinking carefully about, okay, here's what I want to study and I'm interested in. What are the other things that are kind of unrelated to that might still account for variability in my outcome? Measure those if you can and include them because it'll do you favors and make you give you more powerful models. Now you'll see that this assumption is asterisked here. That's because the inclusion of relevant predictors is not a testable thing. I mean, there are tests you can go through and sort of think about and sort of give you suggestion that maybe you have sort of unmeasured variables that need to be in there. But this isn't something I can look at it and sort of get a statistic and say like, how many variables have I missed out in this thing? There's no way to do that, right? This requires you to have a good understanding of your literature, of your area, sort of what you're going through your theoretical models to say, boy, we should have these things incorporated in here in order to have an appropriately specified model. Okay. And the consequences of misspecification, this is complicated. All sorts of biases and also aspects of estimation, right? So I can't even predict what's going to happen. Like, oh, I forgot 3 predictors, so it's likely to inflate my standard errors, deflate my, who knows the hell what's going to go on with this, right? It could go all over the place. And if we work in areas like econometrics or something along those lines, anybody take an econ class in undergrad or in high school, anything like that? Okay, those folks start to become very concerned about error structure specification and things along those lines, because what they're trying to do is identify causal relations between things. Psychology, that's a dirty word. We would never say in a regression model that we're going through and creating sort of testing causality in anything. But for them, that's what they do all the time. And there's some elaborate models to go through and say, hey, if I've gone through and I have this predictor and I've accounted for any other possible variable that could reasonably account for this relation, then the interpretation I'm left with is I have established something that's causal there. Now they're also working with millions of observations and certain things along those lines, which we don't have access to typically in our area. But I think we should, as researchers in our field, be thinking more carefully about, okay, here's what I want to test. What other things should I be measuring to go through and account for variability in my outcome so I have a properly specified model given the theory that I'm working with. Right? The downside of this is you don't want to have, again, if you're sort of looking at well-being, you don't want to have neuroticism and depression and self-esteem and sort of 7 different variables that are all stacked on top of one another, all accounting for the same proportion of your outcome, because that'll screw you over. But what you need to be thinking about carefully is if April, you're thinking about, okay, like what do we know about suicidal ideation? What are the factors that go through? And so here's all a whole list of things that sort of people know and we know is related. Let's make sure that we have these in addition to the one thing that I'm also interested in as well. Questions about errors being uncorrelated with our X's? Okay. All right. Last one. We have 0 population error, right? What we're saying is the expected value of error in the population is equal to 0. So if I've gone through and not violated my assumption, it means that I have achieved specific relation between X and Y in the population with this, right? The error that I'm getting in my model is identical to the population. And on average in the population, sometimes I'll miss high, sometimes I'll miss low, but I'm right on the money with this, okay? Now, if I'm looking at my procedures for OLS, so if you go through, run your OLS regression and look at your average error in your OLS regression, it will always be zero because math works and that's how the whole thing works, okay? That doesn't mean you have not violated assumption. So what it does do is it means that we can't test this again in our data set. There's no way to test this, right? It's an assumption of the model, but there's no way we can go through and test, okay? So let's say, for example, here that I'm going through and I'm looking at the relation between height and weight and that's simple regression model. That's what I want to go through to do. So I go through, bring everybody in, measure them height, measure them weight, and sort of I've measured it without error or as close as I can because I'm measuring physical characteristics. I'm feeling pretty good about this. It turns out my scale is 5 pounds heavy, okay? What I'm going to see is the relation between height and weight is probably going to be unbiased, but my intercept is going to be biased, right? Everybody's going to be 5 pounds heavier than sort of what they are actually in reality, okay? So my errors that I'm getting, or sort of my readings get out based on my model are not going to be equal to zero in the population because everything's going to be +5 on things because I've got a biased measure here, okay? Or let's say, go back to MH is working in schools, looking at aggression and sort of going through and measuring some of this stuff, right? If you're in sort of a school with sort of not that many kids and everybody's kind of well behaved and there's maybe like 1 or 2 instances of this that happen all day, all recess long and you're observing it, your measures are going to be pretty good, right? If you're out, big public school, you got lots of kids with lots of stuff going on and everybody's punching and kicking each other right, left, and center, and it's just you trying to code everything, lots of error, right? Because there's just too much, you got overwhelmed and there's no way to go through and get this, right? So what we'll see is that we will see that your level of error is going to be systematically associated with how much of the thing it is that you're trying to measure. And so all of a sudden we've got a systematic bias in your model, right? So your expected population error is not going to be zero. It's going to be sort of greater, right? Because you're underestimating things, right? There's all sorts of stuff, sneaky ass kids doing stuff that you didn't even catch, right? And so you're like, it's this level and it's actually this level because you didn't catch it. Yeah.
Question about how this is different from the part in assumption number 1 where you measure it without error.
Yeah, this is thinking about with that one, we're talking about individual X's. This is for your overall model.
Oh, okay, so this one would be like systematically our error is trending in this direction in a way it should.
Yeah.
Okay.
So if you were to go through and apply, so you go through, let's say where you've got a sample of 100, right? And you get your estimation of your model, right? And in this case, again, you're doing this, right? So you go through, if we were to go through and take your estimates of your model here, and then just go through it and do it, and then you were to do it again, and then do it again, and do it again, and do it again, what we would find is and applied that to the population, it wouldn't be zero, or you wouldn't your population error wouldn't be zero, and sometimes you're high, sometimes you're low, but sort of everything's sort of you're right on the mark with this. You've got a bias, you're either missing high, you're missing low on this, and so across the sampling distribution of your model sort of applied to the population is going to be off base with stuff.
Okay.
Okay. Whereas before we're talking about individual X's, this is talking about your overall model.
Okay, thank you.
So again, here violations produce bias in your parameters estimates, your standard errors. The nice thing about this one is it's generally not too bad, right? These are tolerable, right? And most of the time what ends up happening is you end up with a bias in that intercept estimate. Are you often concerned about the intercept? Generally not, right? And so it's a violation, but it goes through and it impacts sort of where your line is at more so than how your line is shaped. So again, something that we can't test in our data, something that is an assumption of our regression models, but sort of with this one, you got good samples, you got good methods, you got good measures, and you've got appropriately specified models. This is something that we can kind of not worry a ton about probably. Questions about this? Okay. So we were going through and thinking about our assumptions, okay? Violations of our fixed effect assumption, right? Here, this is okay so long as our data are variable, our data are multivariate normal, okay? And we're saying here each variable, linear variable, each variable linear combinations are normally distributed and homoscedastic, okay? So now all of a sudden, what happens here when we switch over into regression land, now we do have to be worried about the distribution of our variables. Last semester in means-based stuff, had a lot of tolerance with that because we were looking at the distribution of sample means, right? And we know that becomes very normal very quickly under sort of conditions that are easy to achieve. Here, now what we need to do, because we've got our original set of violation of fixed effects, we're actually using random effects or random variables in a fixed variable setting. We can do it so long as our data are normally distributed and all combinations are homoscedastic. And then what we also need to see is our residuals are normally distributed and independent. Okay. What we did is because of this is now we added in some other things that we need to see in order for us to have maximum confidence in our outcomes. Our linearity assumptions pertaining to our normal heteroscedastic errors, we're going to look at some residual plots with this, okay? And we're going to go through and eyeball this. Is there a test to go through and tell me that there's a problem? No, or not good ones at least, right? This requires you to just start to get sort of traction and sort of experience in looking at these. What's a violation that's going to be problematic? Do I understand why there's a violation? If it looks like there's something there, what's the likely impact? And so we're working through some of that. So again, we're looking to look at some scatter plots, some probability plots, histograms, all stuff that you looked at before. We're just looking at it for specific characteristics with your residuals. Okay. Concerns with independent errors. This is generally limited to the type of design you've got. If you got a repeated measure design, you're going to have probably temporal autocorrelation. You need to choose an analysis that accounts for that, right? If you've got data that has nested structure, you're just going to have to, you should know that, and you're going to have to go through and take a look at and sort of switch over into something that accounts for some of that hierarchical structure. So your repeated measure longitudinal designs, right? I'm probably not going to go through and collect EMA data and just like force it into an OLS regression. You're going to have estimators and sort of a platform that is accounting for that, right? Same thing with hierarchical data. This is something you run into if you try and sort of force something in a regression model and then put it up for review. If you got a savvy reviewer that's like, oh, no, you can't look at those type of data with that type of model because there's problems with that. You need to go through and use the thing that's more complicated. So, but super cool. Questions about assumptions, sort of the stuff that we've gone through here. What we're going to go through and do with the next section, we're going to go through and look at in like actual data, what's the process of going through and screening and checking stuff. Feeling okay? Who's feeling overwhelmed? No one's feeling overwhelmed. That's awesome. Cool. I'm gonna assign that to my teaching prowess. Right, I've directed this knowledge directly into your brains, and it's there forever. Cool. All right. Question for you all. It's about quarter after. Looks like we can do two things. We can take a break right now. Now would be a good time, sort of in terms of material to take a break, or we can keep going for another 15 minutes or so, so we get to where we get and take a break there. Go on now or later.
Now, right?
Say now.
whatever I want.
Yeah, let's do it now.
Yeah.
Let's go.
Yep, let's go. All right. Now, so come back in 10. No, I did not. Yeah, no, that's what I've been trying to go through. I'm like every evening, like I'm actually using that as a avoidance of other things that I need to do. Yeah, because it's relaxing and sort of like how you go through, but, no, the issue is we got all this stuff, like the paper pencil stuff like that is integrated in. It's just sort of all the stuff that we've got online, trying to get that sort of integrated in and then this. So keep working with the stuff, the bigger set that we'll have will be sort of, that's fine. It's just, yeah, when I get that knitted together and go through, track some of this down. Every time I think I'm about got it done, then it's not. So other things will pop up and sort of big errors come up and, instead of say, these are not uniquely identified. So, but I'm working through that and I'll just get that kicked your way. Sound good?
Yeah,
Awesome.
I just was searching for your email and I was like, I know he pulled it up,
Yeah,
but also I
yeah.
don't, that we have that data set.
No, and it's, again, once I'm gonna have to think carefully about. And because it's a pain in the ass for me is not a reason not to do something. But like thinking about like as we move forward, like I was like, oh, well, we can go through and we can just do if it's easier for people and it gets them in, we can just run assessments via Zoom. Have you done any Zoom interviews?
Yeah, all cases were Zoom.
Or no, for our project?
Oh, no, not for ours.
Okay.
No.
Yeah, I don't know, and maybe that's something we can sit down this summer, talk about kind of the procedures, because like, it starts to become tricky if, like, you and I are sitting there, then I can go walk through the consent form and sort of
Yeah.
get your stuff, and I can go through, take a look, make sure that you're not gonna hurt yourself or things along those lines. But if you're doing it virtually,
Yeah,
like, and so what we've got is I've got it set up in, Google Forms, so that if, so you're a participant, I can go through, do all the consent process and then say, okay, here's a link. Go through and work on this, and then once you get done, I can just look at it in Google Forms to go through and see, which is fine. But the interface is kind of clunky.
Yeah.
And sometimes it doesn't translate back and forth, and so trying to figure out, like, are there ways it should streamline? I mean, because the big thing is how you go through and pull that up and look and see in real time to see if
yeah,
how people are doing it. Like you do it in Qualtrics because you can just kind of pull things up, but that also can be slow. And then also you would need access to sort of different people's like Qualtrics account to be able to go through and do that. And then if
Yeah.
multiple people are doing it the same, like it gets weird and tricky there.
yeah. It's definitely easier in person.
Yeah, yeah. And I think honestly, I think a better experience for participants too.
Yeah,
You know what I mean? And if you go through and look at sort of people who identify and sort of indicate that they would be up for being contacted for future projects, there's a noticeable difference between people who finished online versus people in person. You know? So
I think it's a good in person.
Yeah. So I think in general, just to say like. Also too, just in terms of, but if something were to happen into the liability, like having people
Yeah,
physically present, so is an easier thing to manage than someone's out in the universe. So, yeah, I think unless there's a very, very good reason for doing it via Zoom,
yeah,
we don't need to sort of do that. So, but this one, we have sort of multiple semesters of sort of data that came in online that's get integrated in. So, but making progress and we'll keep that over and get it sort of squared away.
hopefully that file's the key.
What's that?
Hopefully the file's the key to all of it.
Right,
and
it's gonna
then
unlock the
just
whole thing, right?
Type that in and then everything,
Right, yeah,
yeah,
yeah. No,
That'd be
what it'll
great.
probably mean is tracking down, figuring out in the tracking sheet who the person is or who are we missing, right, in terms of, and then going back through, so.
oh,
That's so awesome.
Okay,
I'm great.
Yeah.
Well, this one is empty and, no, this one is empty. Or almost empty. Yeah, this needs to go in the garbage. Sorry, are you jealous of my peppermint outsides?
Yeah.
Do you want one?
No, I'm okay.
Peppermint
Thank you.
outsides? You already have one.
I miss Trader
I have
Joe's.
I have another one.
I did not see your text from Tuesday.
Sorry.
Here. This is the new box that's not covered in peppermint dust.
I only got the Trader Joe's once when I went back home.
I
Four times.
was gonna go, and the one time when I was like on a path where we were walking by Trader Joe's, they closed early.
Yeah, I know they
That is so I couldn't go.
Even other places they close it, now I start stop it. Like I'm.
No, it was like in the middle of
going out.
the day and they were closed and I was like,
I can't.
body is like hanging on.
Every time I go, I think over break I went. Here's one time I was like 2 p.m. and I was like, oh, there's not meeting there. There's like so many people. I
Do
just
you all wanna be jealous? Do you wanna know what Dylan had for lunch?
Oh, I would know.
Bread, cucumbers, fish sticks, french fries, milk,
I like that. Champion.
right?
Cheddar cheese pretzel.
I had a strawberry.
8 PM starting, tostadas. Salt.
For breakfast. Like, I love that.
Breakfast, kicks, milk, strawberries, so.
I like the specifier.
Right?
I like
Yeah.
strawberry.
Get all her fish sticks, but
It's like-
some of her kicks.
She's cute.
Applicants told me that they're just like, I need the red dye that she used to make that, and I was like, oh my god. I'll take red dye.
It's the red dye, it all red dyes. It's like red.
So I was like, you already made the process, my body has like, so like, if they're having Caesar salads, I love their dressing. It's so good.
It was so good. Government knew about this and they literally were. Interesting.
No, you know what?
2025 Miami girl.
The way out.
What, the world?
The way that everything is just like breaking. Oh my god, I literally can't. That news.
So like,
It's not like more cheese, like, no. it's not
This
one of
is
those.
goat cheese.
Oh, in the middle of the bread.
These are red. And then you dip the garlic bread in the goat cheese.
like you were responsible. Like, but
I have to sit there.
I need to know why you got really
It's like close the eyes.
I literally just like don't feel so bad for other people. It's workable with other things. You know, it's like we're just like these words. I tell you that you're bad at your job. So you upload it here. And I'm like, yes.
All right, folks, so let's, we'll jump back into the middle of this, we'll leave the door open for Lieutenant to, come back, but here we go. Over yours, if you'd like, I'm gonna go through and reporting. Oh, no, I guess, oh, no, I'll fix that later. I was recording the whole time. I stopped the screen share. Okay.
That's so sad.
I always got that.
Yeah. It's a nice place. It's a little bit similar to Altitude.
Never actually.
Where?
The Rib and Trump House.
Wait, that's yours?
Yeah, it's down Grand.
Really?
It's a chain, yeah. So I think I saw one in like, shine, like, I got.
Well, I trust Mason's dad.
Question, do you have an idea on how I can, pause my screen share here?
Unpause what?
Sometimes you have to like
so
escape
you
the
can
full
get-
screen and then go back into it.
Okay.
Right, hitting resume.
Stop share. There you go.
Yeah.
Like this.
It's.
MH's tech support, she's like, is it plugged in? So
Turn it off,
here-
turn it on again.
I know why they're asking, but it makes me really mad, like, yeah, you know what I mean? Okay, so what we're gonna do is we're gonna go through and work through in slides. Just with a set of data to go through and kind of walk through this process of going through and screen. What we'll do afterwards is go through a actual SPSS example, but just to get concepts down. What we've got here is just to give you an idea of like sort of we're setting up this regression model. We're interested in the unique associations of psychological flexibility, okay? Reward responsiveness, how sort of like jazz we get about sort of responding to sort of good things and rewarding stimuli, some behavioral inhibition and willingness to utilize social resources on perceived social support. Okay, this is just like convenient. This doesn't. I mean, I guess it kind of makes sense. It's not a great question, but it's more about like here. Can we throw some variables to take a look at stuff? Okay. So again, here are our individual variables. Our MSPSS. This is our social support measure. This is our outcome. Okay, and then we've got 4 predictors right here. So we're going to go through and look at this and write this out in a model. Do this. Get used to this. Be comfortable with this because this is going to be really, really important as we get into moderation stuff. So we've got our predicted value of our outcome is going to be a function of our intercept. Okay, this is our starting value, and then we're going to make adjustments up and down based on our other predictors. Here's our psychological flexibility, our reward sensitivity, behavioral inhibition, and our utilizing willingness to utilize social networks. And then here on the end, this is our error term. This is our residual. This is what we're going to spend most of our time worrying about right here when we get into nesting with the actual stuff. So approach for screening is going to be the same thing we've done up to this point, right? What we want to do is we want to go through, look at accuracy, plausibility. We want to look at missing values. Here's something I had mentioned before. When you're doing your missing values, also know what variables that those data are missing on. Is it missing on everything? Is it missing on certain things? Like who is missing? This starts to give us an idea about the mechanism of missing this that starts to become important, right? If you've got a sample of 120, you got 5 variables that you're going to exclude because of missing data. It's not a big deal, right? Unless all 5 of those variables or all 5 of those cases are missing the same variable, come from the same group. Now all of a sudden that's starting to suggest like maybe there's a pattern, right? So we wanted to keep an eye on that. Univariate distributions. Again, before last year when we were looking at t-tests, ANOVAs and things along those lines, I had a wide tolerance for what we're going to accept in terms of meeting sort of as being fine. Because again, at that point, we're thinking about is the distribution of sample means normal? Here, we're literally talking about sort of what we're looking at, right? So we need to be more careful about stuff, and you'll see the impacts and violations as we move forward through different examples. We're going to look at univariate outliers, and then we're going to look at the linearity or skedasticity of our bivariate plots. Okay. Again, remember, in order for us to assume that our data are multivariate normal, we need to have all variables have a normal or reasonably normal distribution, and all linear combinations are all combinations are linear and homoscedastic, right? So we don't have nonlinearities in there. We don't have probably homoscedasticity. Now at the observed level, if we see evidence of homoscedasticity, we want to flag it. But what we're really most interested in is whether or not we have homoscedasticity within our residuals. We'll get to that piece of things. Okay. So here, wanted to go through looking for multivariate normality, but again, also looking for possible specification error. So if I'm seeing heteroscedasticity in a bivariate relation, it says maybe suggests that there's something missing out of my model that might account for that. It should trigger kind of a thought process for you all. So, for our univariate distributions, I got some data output, which is fine. That to be out of the way. All right. So we go through and take a look, again, here's my model. Within this table, and so the one thing with this is, in state neutral kurtosis is a value of 3. So take that, take the value here and subtract 3 from it. That's your sort of kurtosis value that you would get in SPSS. Are there any sort of major concerns in these data with my distributional indices here, skew and kurtosis? Things are looking pretty good, right? Not too bad. If I'm going through, I might flag and say, oh, SPSS has sort of some negative skew there, right? And negative skew suggesting that most people are reporting high levels of social support. And then we've got kind of a negative tail, like some people are sort of feeling a little bit low, but, and maybe some in reward responsivity, some negative or negative skew with that. But overall, looking at this, there's nothing in here that would cause me a ton of concern, right? At least from sort of the index standpoint, okay? But if I go through and I plot this out, now all of a sudden, right, we start to see a pretty obvious skew with this, right? And again, thinking about what's going on and saying within the sample that I've got, most people, thankfully, are reporting high levels of social support. They're feeling pretty supported. We kind of hit a ceiling on the top of that. And then if people are sort of, our variability is going sort of downward here. What I've got in Stata is this is just a kernel density plot to just kind of see kind of where that's at, right? So again, thinking carefully about, yeah, our rules of thumb say skew less than absolute value of 2. But just because you have a skewed value that's less than 2 doesn't mean that you have normal data and you shouldn't describe it as such. You need to be looking at plots and saying like, well, so we would have this kind of within normal expectations, but we are seeing some negative skew to this. And you'll start to see that this carries forward and has implications as we move forward, okay? Here, what are we measuring here? My AQ total, right? So here, much less skew, a skew of 0.3, but still, we've kind of got sort of a low end and things kind of going down, right? Here is my reward sensitivity. Here's my behavioral inhibition. That's actually looking probably about the best one. Oh, that one's all right. And here's my sort of willingness to utilize support. Okay. So again, just wanting you, just like we did last year, to go through, look at your histograms and so the combination of these, going through and saying like, here's what we kind of got going on. Now, there's nothing in here that's necessarily disqualifying or problematic. I wouldn't go through and transform any of this stuff, right? But what I should be doing is recognizing that I've got some potential issues with this. And now if weirdness starts to come up down the road, remembering back, oh, that bass reward was kind of weirdly shaped. My outcome was weirdly shaped, things along those lines. Other thing too, what's the other thing too? So we've got some, there's not much in here that I could with a straight face identify as normal. What do I have going for me in these data? Yeah, exactly. I got 335 people in here. For us, that's a pretty big sample. That'll shoulder a lot of stuff that comes up, right? Where I would start to maybe become more concerned with these distributions if I had a sample of 40, 50 or something like that, right? So again, wanting to take this context into account. Okay. All right, going to switch over, look at extreme values, linearity, homoscedasticity stuff, okay? Again, this is stuff I ran in Stata here. Any concerns with extreme values? What do you think, Danielle?
What I can tell, looking at the mean max. Doesn't seem like it. To be fair, I don't know like what the scale is.
Okay, so these are Z scores.
Oh,
these are
okay.
Z scores, yeah. So looking at this, anything you might flag in terms of larger Z scores?
the MSP ESS is higher compared to the others.
Yeah, I got it, so the negative value of like 3.7, 3.8, right?
Seems to have a more extreme value than
Yeah, right.
than the other.
And then sort of maybe I could point to NOS and say, you know, if we were using like 3.29 or 3.3 or something like that, it's sort of corresponding to P equal to 0.001, right? These are starting to get sort of bigger values. So yeah, I might go through and in the screening, sort of flag some of this stuff. Why might I not be too concerned with this? What do you think, April?
I guess because you have such a large sample, you're inevitably going to get some people who are kind of on the far end.
Exactly, right? So again, what I wouldn't do is freak out, start lopping off people as being outliers, right? I got a huge sample in here, right? So this one person has a very low MSPSS score, right? And if we go through, and that's this person right here, and they are an outlying value, and so they're sort of notably low, right? I might go through and check those data to make sure that they are correct, but certainly someone cannot feel supported, and that's a real value, right? But I got a whole, like these two people are not gonna screw with my sample, right? They're not gonna drag my mean off base, right? And with a sample of this size, wanna note it, say it's there, and this will start to become important as we move forward in our screenings, because what we're gonna look for, we're looking to look for weird cases. Where are those existing and how are they popping up? Again, you'll see usual suspect stuff. The same people will keep popping up again and again. So what you should be doing this semester as you're working through this, if you start to find these cases, just keep a running tally. So this person, case number whatever, came up as an extreme value. I'm not gonna like do anything with them, but I just want to keep an eye on this person. Because we get a repeat offenders keep coming up, and if they keep popping up again and again, then you start to say maybe like, do we need to have this person in there? Now, probably in a sample this size, like this individually is not problematic. If I start seeing this person pop up in combination with other things that start to make me wonder whether or not they were reading things carefully and they're having plausible combinations of variables that wouldn't make sense given what we know about stuff, maybe I start thinking about, I don't know if Broseph was paying attention to this as we were going through, so we're gonna take him out of the mix for reasons, right? So other thing what we're gonna do here, so we're going to go through flagging, sort of check some of our extreme values here. Then another thing we're gonna do go through is gonna pop this up. And again, sort of because we an assumption of our multivariate normality, we need to have linear relations and linear and homoscedastic relations between all combination of variables. What we're gonna do is we're gonna go through and we're gonna create a scatter plot, okay? And we got this plot matrix that we'll go through and kind of say, okay, are there things that I might want to go through and take a closer look at, okay? MH, or you say, I'm just like, you're making expressive faces. Is there anything in this plot that you would sort of maybe have some concerns about or want to say, like, boy, I want to zoom in on this?
Middle row,
Which middle?
like the horizontal middle row.
Oh, this one right here?
Yeah,
Okay,
just, I don't know if it's like the way that it's graphed, but with like almost like clearly delineated like horizontal lines seems kind of,
yeah, so here and here.
yeah, concerning to me. I don't know if that's like,
Yeah, no, what's going on with that? You're right. That's an observation that you should be attending to. What is that? What is that telling me about these data?
I'm assuming it's something about like the scaled measurement and how people have to fall on one point or another, like a Likert.
Like this is what it is, right? Like it's not a continuous variable, right? MSPSS, this is a mean, right? So you can take any values. This is like you have discrete values. So what I don't have a continuous variable here. I have a discrete variable. Now, this is a discrete variable that takes on enough values that we can treat it as continuous and probably be fine with that. But the consequences is it's going to start to give you kind of these lined sort of types of things, right? So being at least aware of that, sort of marking that down, being, hey, this is something that's going on, right? Now the upper diagonal, lower diagonal are fine. They're just kind of flip-flopped on one another, but we can start to see sort of that as a thing. Is anybody seeing anything that's looking problematic in terms of a clear nonlinear relation in any of these scatter plots? Any clear curves or anything like that? I'm not seeing anything. Now, what can start to happen is you get really dense data, right? And lots of observations. If things are really highly packed, it can sometimes be hard to see if there's like an underwater stream kind of going through stuff and things are really tightly packed. So there's some things we can go through and do to try and see if there's anything going on there, but visually doesn't look like there's anything going on. Are there other things that people might be worried about with this in terms of homoscedasticity? There's some stuff I might want to go through and take a closer look at. Yeah, April.
I was gonna say, the second box, it looks more. The one on the top, the second one in the first row, sorry.
So
Up and then over to
There
the,
you go,
yeah.
yep, that one. I was
Okay.
gonna say that one looks tightly packed at the front end and then it starts to spread out a lot.
Yeah, right. So maybe we're starting to see some spread here, right? And so thinking about that, right? Like here, it's kind of hard to tell, right? What we're doing here is we're going to go through and identify, is there anything going on that we need to have a closer look at? Then what you can do in your statistical program is just look, okay, give me the plot of this and this, right? Then we can go through and take a closer look. Sometimes things look like they might be suspicious here, and then you go through and make, oh, I guess that's fine. Right? If we go through and we take a look at, what is this? This is the relation between NOS and NOS PSS, this one right here, right? Is again, I've got kind of a densely packed things and then things get a little bit spread out in terms of stuff. What I can do is I can pop up that individual graph and then go through and see. And here's my regression line, right? That's my straight line here. This red line, this is the lowest line that's going through and sort of mapping kind of best fit in a curvilinear stuff. We get a little bit of a curve down here to the end. But again, I'm not worried about that too much, right? If I'm looking at around this line, distribution gets sort of reasonably fine, so I'm okay with that, right? So overall, if I was looking at this, I'm like, is this maybe like a curve? If I'm just looking at this, I might wonder if is this like a curvilinear type of thing? I can pop it out, regression line through it, run a lowest curve through there, and I say, yeah, it's actually not looking too bad with things. So do people see what we did there? Okay. Something I might sort of be kind of worried. We got what's going on with this, right? We got kind of everything's kind of packed up in what I'm measuring. I've got AAQ on this dimension and my behavioral inhibition on the other dimension. So let me go through and pop this up, right? I want to take a closer look, right? Well, when I do that, it's actually not as bad as what it looks like here, right? It's again, very clearly sort of that line is running through it. That's fine, right? I get one with my lowest, it kicks up a little bit, but that's just grabbing points at the top that are sort of going through and influencing that. Looking at this, my concern might be heteroscedasticity, because it looks like, boy, a whole like thick stuff down here and very thin towards the top. But if I sort of zoom into that, it's not looking too bad, right? Here at the end, I'm very clearly sort of missing some stuff. Why might I not be too concerned with what's happening right here? Do we have much representation at the top end of that? Would I expect without too much representation, a whole big sort of variability up there? Not really, right? So it's really, if I'm looking at sort of, again, variability around this, I mean, it's very clear. It's more here than it is here. We're looking like a 3-to-1 difference in terms of metrics. Here, yeah, it's very small and that's very clear, but like, I don't have enough data here to actually sort of make an inference on anything. It's just sparsely populated up there. So again, this is something that I would for sure want to look at, but when I actually pop it open, I'm like, okay, fine, I'm okay with this. All right. Questions about that? Just going to see what we're doing in terms of our screening. What we're looking for in terms of sort of this is, so we've gone through and we've looked at our distributions, extreme values, looked at our bivariate plots to make sure everything's looking good, right? What we now need to do is we need to switch over and sort of run some residual analyses. Okay, yeah.
I just realized I had a question about the
Yeah.
skedasticity screening. Like because these are all individuals, like each individual score on, like each measure, like so for instance, the one on the top, like the first one like that one is like the MSPSS
Yeah,
on the
NOS.
Y and then the NOS.
Yeah.
On the X, if there's a missing value on one of those, would the person not be included?
Yeah, you would see that. So we would go through and so this is 100% something that you should be doing on the front end. And this is great, Lucy, yeah, on the front end, identifying who we don't have full information for. If they're missing a value on one of the predictors, then they can't be in the regression model. They're not going to get included. So it doesn't mean it makes sense to include them in the subsequent screening. So just as we did last semester, we would say, here's a person who doesn't have who has missing data, mark the case, what we saw in terms of character, what they were missing on characteristics, and then exclude them from the set. Yeah. Because otherwise, and this is a really good example, because otherwise when I'm doing this, I would like to say, okay, what's my functional sample? Who's eventually going to be included in? Then otherwise, I'm going through and doing screenings and identifying people who are univariate outliers on stuff when that person is not going to be in the analysis anyway, because they're missing something on something else. So reducing that down into a set, but then also making very, very clear that you're keeping good notes about who you excluded and why. Because I will guarantee you'll come back to your project 6 months later on the R&R and have to figure out like why you threw somebody out, and then trying to recreate that takes 3 hours of your day to try and figure out how you got back to that. So take good notes about that. Okay. So what we're going to do then is we're going to switch over and we're going to run a regression model. We're going to request that SPSS save the residual values. Okay. And what we're going to do is we're going to go through and look at those residuals. Okay. And this is a really nice kind of diagram, stuff that we're looking at, because there's a lot of different characteristics we want to see out of our residuals. If we're looking at panel A right here, what we're doing when we're plotting out our residuals is our x-axis is our predicted value and our y-axis is our residuals. Okay. So x-axis is y hat essentially, right? And what we want to see is something that looks like this. Okay. Here, as my predicted value increases, we're seeing my residuals pretty tightly packed around that line. As they sort of get out, they start to spread out. If I look, I've seen uniform distribution of this across all predicted values of y. My residuals are about the same shape. They're normally distributed. They're sort of evenly distributed. Here we've got normal and independently identically distributed residuals. Our assumptions are met. We're really excited about this. This is looking good. Panel B, here we have non-normal residuals. Okay. We have residuals that are still stacked around our prediction line, which is sort of expected and around 0. But when we miss, we're always missing. We're missing high, right? And people are falling below that, right? If I were to go through and take a look for any individual predicted value of y, my residuals are skewed, right? And so this is going to be a problem here. What I'm worried about is I'm going to have attenuated standard errors here, because my residuals aren't normally distributed. Here in panel C, we're seeing and something going on there. There's something nonlinear going on in these data. My residuals have a very clear U shape, right? And this is why it's cool to go through and take a look at this, because what I might find is no evidence of nonlinearity in any pairwise plot of anything. But when I throw this into multivariate space, there could be something that pops up that I see that I couldn't see in my individual pairwise comparisons or my pairwise plots. There's something nonlinear going in there. I need to be thinking about, like, if I have a correctly specified model with this. And then here in the last panel D, I've got heteroscedastic residuals. Okay. As my predicted value of my outcome increases, my residuals get bigger and bigger, right? Again, still mapped along 0, but I've got much larger residuals at the high end of my predicted value than the low end of my predicted value. So in here, in this case, we would see attenuation of my standard errors because as my predicted value increases, my residuals fan out. This is going to result in a depression of your standard errors. If it was the opposite, if it started big and sort of narrowed down, we'd expect inflation of my standard errors. I got kind of the opposite direction, a very clear violation here. Okay. So again, and we're looking at heteroscedasticity. It doesn't have to be identical across the whole thing. What we're looking at is something sort of in the sort of mark about 3 times greater at the widest and the most narrow, recognizing that this is the widest and the most narrow, we have reasonable representation, right? You wouldn't want to catch a sort of bald spot in your data and say like, well, there's only sort of this much variability there. You don't really have representation. I would be careful with that, right? So again, what we're looking at is some pretty noticeable and obvious violations of homoscedasticity. That's something you would note and flag. People seeing the different patterns that we'll be looking for in our residuals. Questions about this? Yeah, Emma.
So if we were to like apply the rule of thumb roughly to figure D, when you're saying not picking a sparse part of the data, where would you select the most narrow point on that?
Yeah, I mean, this is pretty good because it's just an example and things
Yeah.
are pretty evenly. So I would
Okay,
say,
so back at the
like,
beginning.
yeah, here, you know, we're
Where you see
saying,
those dots collecting. Okay,
yeah, this is about this, and this is obviously
yeah.
more than 3 times that. This is a pretty obvious sort of violation, but this is kind of the types of things we're looking for. All right, other questions? All right, so we go through and we run this in our actual data. This is what SPSS is going to give us, okay? Here, we've got our standardized predicted values. This is our standardized Y hat. And then what we're doing here is we're requesting, here are standardized residuals, okay? What are we seeing in this graph? So again, here's my 0 line, right? The mean in OLS regression, the average of my residuals is by definition 0, right? So things are going to cluster around that. But again, what we're wanting to see is evidence of normal distribution, even distribution across your residuals here. What have we seen in this plot? And then this bent line, this is our lowest line. This is our like line of best fit that's going through that can kind of curve around and things. What are people seeing? Yeah, Lucy.
You'll seem a little bit closer to 0 as X increases.
Okay.
Or sorry, as the actual Y increases.
Mhm. Okay, so this is predicted Y, not actual Y.
Sorry,
Yeah,
predicted Y
yeah.
increases. Yeah.
Yeah, is there anything in this that is standing out to someone as weird looking? Yeah, April.
I don't know if this is what you're getting at, but the top part of those dots looks like it's hit the ceiling, like it's all in a line. I don't know if that.
Yeah, something like a weird kind of shelf going on right here, right? And yeah, that's not supposed to do that. Like what's any ideas on what's happening if we think back to our distribution of our observed variables, something that might be causing kind of what looks to be a very clear kind of linear shelf right there. What's that?
The skew.
Of what?
This MSPS, yeah.
Right. So we see here, right, we've got a hard ceiling on this, right? And then, so we've got sort of things skewed down negatively, right? And so if I go through and I take a look at my actual residual plot here, right? What I've got is I've got sort of a top end, right? You can't get larger than the top end, right? And so here's my predicted values. If I'm thinking about this, my predicted value of Y, and this is my residual, right? We're seeing as my predicted value gets larger and larger and larger. So these are people who scored the top value, right? And so for this person right here, my model says they should be down here, but what they actually did is they scored higher at the very top. And this person scored at the very top, and this person scored at the very top, and this person scored at the very top, until you get down here around here, and now you got kind of people who are actually at the max value, right? And so what you've got is a kind of this hard line that as sort of slopes down to perfect prediction, but these are all people who scored sort of at that top level. But here, model just underpredicted until we get to this point, right? So what we're seeing here, and this is why it's important to take note of what we're seeing in our observed variables, is we're seeing a direct impact on the shape of this distribution based on what's happening, okay? And so again, if we were to have an outcome that had a nice sort of normal distribution, we'd kind of probably still have sort of this type of thing, right? So what do we do with this, right? I could make an argument, I suppose, that if we're looking at the sort of spread here versus the spread right there, then we have evidence of heteroscedastic residuals, but not really a ton of sort of information right there. So I might be worried about taking too much. If I'm taking things from here to here, it looks like they're reasonably kind of similarly distributed. When we get to start at this level here, I might be worried about sort of maybe that we might have residuals that are not completely normal in terms of their distribution. And so with this, what I might go through and be concerned about is, given the ceiling on my outcome for portions of this, I might have sort of some problems with non-normal distribution of my residuals, which then, so we know, it sort of results in attenuated standard errors. So I might go through and mark that down, right? Now, is this a function of like the actual phenomenon? No, I don't think so. I think it's a function of my measurement tool or the population I've sampled, where most everybody's just doing pretty well, right? And so I can't miss high. I can only miss low, right? And so kind of seeing what we've got going on with this piece. People kind of see the logic I'm sort of working through with this. And so again, here, if we look at this residual, remember that our residuals are calculated as my observed value minus my expected value. What I've got is an under prediction, right? This is someone who scored very high on the MSPSS, like most people, reporting good levels of social support. But based on their other factors, I would expect them to be down here. So I've essentially under predicted sort of this person, right? Contrast, here's an over prediction, right? I think my model said this person should be up here. They're actually way down here, right? And so what I've gone through is sort of missed that person in the opposite direction.
Kind of backwards.
Yeah, it is a little bit backwards, but sort of write this down because it starts to become important in thinking about when you're identifying sort of points and large residuals. Conceptually, it's very, very useful to think about, like, is my model underrepresenting this person or overrepresenting this person? Remember that residuals are calculated, raw residuals as my observed minus my predicted. And so that you can go through in detail, like, okay, I've got a large residual. What does that imply about this case? It means my model is saying they should be scoring much higher than they actually are, or my model is saying that they are scoring lower, that they should be scoring lower than they actually did. And so that's going to help you think carefully about sort of who are these people, what's going on, what do I do with them, is it a concern or not? Questions? All right. Yeah, so this edge is just sort of excessive response at the height of my outcome, right? And so what we're seeing here is just a function of my measurement, my measure. All right. Other thing we can go through and take a look at, this one is probably going to be your most important sort of plot that you'll want to go through and look at, right? And again, what we're thinking about here is the conditional distribution of your residuals across predicted values, okay? And what we can see is probably like right here, relatively normal distribution at this point. But as we get down here, we're seeing maybe some skewed at the bottom end, right? So remember, write this down. You're looking at conditional distribution of your residuals with this. This starts to become more important, most important. But what we can also do is we can go through and we can plot our all residuals. We talk about this as not your conditional distributions, but your marginal distributions. Of all my residuals, how are these distributed? It's still worthwhile taking a look at this, okay? What we can do is we can plot our residuals looking at probability plots and some histograms, okay? And again, what we're wanting to see is relatively normal distribution of our residuals across some of these mechanisms, okay? Now, we all know what histograms are, right? If we go through and plot my residuals here, I've got a nice and normal sort of histogram, and then we've got other histograms. You know what histograms are, we don't have to talk about those, right? Now, our probability plots, these are different ways of plotting things to help us gauge normality, okay? We are very good as human beings as detecting lines and adherence to straight lines. What your probability plot is going to do is it's going to plot your residuals along a diagonal line, okay? And in your probability plot, if you've got something that has a nice normal distribution, what you're going to see on the probability plot is something that sort of approximates a straight line, okay? Now, as you start to go through and we're looking at in this second plot here, right? We've got a plot, a histogram with a high negative kurtosis, right? It's basically a square plot. If we go through and look at our probability plot for these data, we're seeing something very different than this, right? We're seeing this kind of sort of curved S-shape kind of thing going on right here, right? Indicating sort of negative violation of kurtosis, or we got a kurtotic distribution with negative kurtosis. With positive kurtosis, we kind of get an inverse of this, right? We get kind of a quadratic thing going on here with a skewed distribution. We're getting a probability plot that has kind of a curvilinear function here. Okay, so your probability plots, and you can have there are different ways of going through and plotting this out. You don't have to worry too much about this. PP plots is cumulative distribution. QQ plots are quantiles. They look kind of the same. Some people will have preferences for one or the other. It doesn't make that much of a difference. But what you'll see is, in addition to helping you with the histogram and kind of looking back, oh, is this normal? Plotting this on a probability plot, and what we're looking at is deviations from sort of that straight line. So if we go through and do this for our residuals, and this is going to be our marginal distribution. Overall, if we look at the marginal distribution of our residuals, not too bad, right? Maybe a little bit of skew here, right? So again, we see kind of this top end that's kind of chopped off a bit, but it's not horrific. It's kind of generally sort of symmetrical-ish, not doing too bad. If I go through and I take a look at my probability plot here, if everything was perfectly normal, it would fall right along that black line. We've got some deviations a little bit, kind of consistent with some positive kurtosis, but it's not too bad. So so my marginal plots, I'm not too worried about this. Questions? Let's see what we're doing with this. Yeah, April.
I guess maybe this would like come with time, but I think I'm still a little bit confused on like when we're looking at the probability plot. What kinds of deviations, like how strong do we have to go away from that line in order to be worried about it? Because this one you said isn't worrying, but the one on the other side was worrying.
Well, I mean, like, so if these are all pretty obvious, right? And with the number of people that we have in the sample, we're pretty good, right? I would say kind of run through sort of the swinging of a pendulum. So most researchers out in the world are probably not concerned at all or even looking at this stuff, right? So that's obviously problematic. Sometimes when people kind of in your area or at your stage of training do get in the middle of this, they start to over interpret things and sort of start freaking out and doing weird transforms that probably don't need to happen, right? So I would say as you're working through, if there's something you need to talk about, it'll probably be pretty obvious, right? There's some weird stuff going on here, right? With this edge, probably need to figure what's going on with that and talk about that, right? And here I would say that we maybe have people in certain spots, we've got maybe some negative or negatively skewed residuals. If we're looking at the conditional distribution of these, it's probably worth talking about. These, nothing, this is fine, right? Your data is never gonna, unless you have really massive samples and well-behaved variables, it's never gonna be perfect. You'll see it in the next example, you get more problems with stuff like this, and you'll see what happens, right? But again, as part of the screening process, you shouldn't be jumping right in the middle of this. If you've got variables that are gonna mess with your screening, you'll have identified those on the front end, and then you see wacky stuff here, you're like, okay, now I gotta go back through and sort of address this piece of things. But as you're going through your screenings, if you have questions, come talk to me. Be like, I don't know, is this weird? It feels like it might be weird. I'll tell you, yeah, that's weird. You should probably think about it, talk about it, or it's probably fine. And this is just experience. You just got to do a bunch of them before you start to sort of get some numbers down. Okay. Other thing we want to go through. So we've gone through, taking a look, plots of our residuals and sort of some made notes of stuff there. What we want to do now is switch over to problematic cases. Okay. And there are different ways that cases can be problematic. Okay. Think of this as, are we talking about X space or are we talking about Y space? Okay. One way of describing problematic cases is with respect to discrepancies. Okay. Discrepancy is determined as the difference between an observed and expected value of Y. We're talking about our residuals here. Okay. So if you have a case with a high discrepancy, what that means is the model is not doing a good job of accounting for that individual, right? The model says they should be here, they're right here. I've got a high discrepancy value. Discrepancy is all existing out there hanging out in Y space. And a leverage, on the other hand, is going to be characterized by unusual combinations of your explanatory variables, your predictors, right? Leverages, this is hanging out in X space, okay? What we're going to do is we're going to go through and take a look at those as a function of leverages, and we'll talk about what those are. Influence, this is going to refer to the degree to which, so whether or not the case is in the model or not, impacts the model or individual coefficients. This is probably the thing you need to be most worried about, right? For any sample, if I put Lucy in, if I pull Lucy out, it has dramatic impacts on my model, right? Even if I have large samples, because one person should not have that much influence on things. If I have a set of results that's entirely dependent on whether or not Lucy and Emma W were included in that sample, that's probably not a reliable or generalizable solution. I need to be thinking about that. Okay. And so this is what's going on. Influence is a combination of discrepancy and leverage. Okay. It's a fantastic set of panels here. I really like them. And I'm not joking, like, I really do like these. It's pretty fantastic. All right. What we've got here is demonstrating some different things. So here's my line, here's my data, and here's sort of a point I've got. What we're seeing here is someone who is high or sort of moderate discrepancy value, right? So here's everybody else. Everybody else is perfect straight line. But then we've got this plot, this observation hanging out right here. If I look at where this person lands in Y space, it's a decent sized discrepancy, right? Here's where they should be. Here's where they're at. So I'm very close with everything else, right? And so I've got a moderate discrepancy, low leverage. Why is this a low leverage value? Is this point weird in X space? No, it falls right in line with it. It's not weird in X space, but my model doesn't do a good job of accounting for this. And I would say low influence, okay? If I go through and I put this, if we have the dotted line is my regression line with that person out, and here's my regression line with the person in, does it impact things all that much? No, it drops the intercept down a little bit, but the line is the same, right? So here we've got someone who is characterized by a noticeable discrepancy. Leverage isn't bad. Influence isn't too bad. It sort of drops, again, my intercept down, but like my actual estimate of the relation between X and Y is unaffected because it's actually parallel there. People see what's going on with this. Contrast with this, okay? Here we have a case. Everybody else, perfect, same perfect straight line. Now we have someone who's hanging out in this space here, okay? Now we have someone who is a high discrepancy, large discrepancy. And then we'll talk about this in terms of different types of residuals. We're gonna go through and take a look. If this person isn't in the model, right? If I estimate the model and then say, oh, hey, what's the value for this person? I've got a pretty large discrepancy, right? So here's where my model expects them to be. Here's where they're at. I get a pretty large discrepancy, okay? I also have a large leverage value. Here's in X space. Here's where everybody's at. I've got someone who's way the hell out here. They're weird in X space, right? And because the slope on my line changes dramatically with this person if they're in versus where they're out, I would say a high influence for this person, okay? Now, here's what's tricky. If I just estimate this model with this person in, what is the discrepancy value for this case? Do I have a large residual or small residual in the model estimated with that case in there? It's small, right? It's almost perfect, right? So if I'm just looking at my residuals, only my raw residuals, this case is not problematic. It looks like I've done a pretty good job of accounting for it. The problem is that it doesn't take into account that if I were to drop this out, the model changes dramatically, right? And so if I were to estimate the model without this in, this is where it should be. What it does is I have a high leverage, a high discrepancy case that's going through and having a huge influence on my model. It's basically dragging everything down to meet that one person when this person is a strange person. Okay?